Bonjour encore, Cern. Je me suis présenté ce matin et maintenant je suis ici pour vous enseigner à tuer les mutants. Les mutants, pas moutons. Mais encore, je le ferai en anglais. So, what on infinite Earths makes mutation testing, on the one hand, different from all the other software testing techniques we know? The big difference is that most of the others are about checking whether or not our software is correct. But mutation testing assumes that our software is correct, at least in the sense of passing its tests. Instead, mutation testing is checking for two other qualities. And in a typical code base, I think the more important one is that our test suite is strict. Now, you might be thinking, isn't that what test coverage is for? If we have 100% test coverage, doesn't that mean that our code is fully tested? No. The only thing that test coverage tells us is that at least one test ran the code that it claims is covered, and conversely, that none ran the rest of it. It tells us nothing about whether or not the correctness of the code had anything to do with whether any test passed, let alone any particular test. And that's what we really mean when we say code is tested, right? By way of illustration, let's look at a test and comment out the assertion. It still runs the function, so it counts as covered, but we're not asserting anything. So the function is obviously not tested. The best we can say about it is that it doesn't blow up. Big deal. So how can we tell if our code really is tested? As you may have guessed, that's where mutation testing comes in. To check that our test suite is strict, a mutation testing tool will try to find the gaps that let our code get away with unwanted behavior. And when we find these gaps, we can fill them in by either adding more tests or by improving and effectively expanding some existing tests. Lack of this strictness is usually caused by a lack of tests, of course, but also poorly written tests or poorly maintained tests, especially ones that didn't keep pace with changes in the code. Speaking of the code, the other thing that mutation testing checks for is that our code is meaningful, by which I mean that any tiny little semantic change, as opposed to structural or stylistic, will have a noticeable effect on the code's behavior. Lack of this meaning, or lack of meaningfulness if you're not into the whole brevity thing, is usually caused by code being redundant or unreachable or otherwise just not having really any effect. And when we find such code, we can look at it and figure if we really want to make it meaningful, make it so if that really fits our desires, but the usual fix is to just remove it. Mutation testing puts these two together by checking that every tiny little change the tool knows how to do does indeed have a noticeable effect on the code's behavior, and that our test suite is strict enough that at least one test will notice that change and fail. Now, that's the positive side. But as Fred Brooks told us back in 1986, there's no silver bullet. Besides, those are for taking care of werewolves, not mutants. The first drawback is that it's rather hard labor on the CPU, and therefore usually slow. We certainly won't want to mutation test our entire code base every time we save one file. Maybe over a lunch break for a smallish system, or a weekend for a large one. But fortunately, most of the tools have ways to tell them, I just want to check this function, this class, this file, maybe this directory, especially if you have a multi-directory project. And some of them have ways to tell them, I only want to check various milestones, like since the last time we ran the tool, or the last Git commit, or the changes from the main branch. With filtering like that, maybe we can check just the relevant changes when we save a file, or at least check it over a much smaller break than otherwise. Another drawback is that it's often not at all clear what to do about the results. It tells us that this change to the code made no difference to the test results, but what does that even mean? It takes a lot of interpretation to figure out what a surviving mutant is trying to tell us. Their accent is very strange, and they're almost as incoherent as zombies, but with a much larger vocabulary, so they're not always on about brains. They're usually trying to tell us that our code is meaningless or our tests are lax, or both, but it can be very difficult to figure out exactly how. Sometimes, even worse, it's a false alarm, because a mutation might not make a test fail, but it might not have really made a difference in the first place. But it can take a lot of time and effort to figure that out. And even if a mutation did make a difference, most programs contain quite a lot of code that we just shouldn't bother to test, like debugging traces and so forth. Fortunately, most of the tools also have ways to tell it, don't bother mutating this line, this function, and so forth. But that's usually done with comments, which can clutter up the code and make it a little less readable. So now that we've seen some pros and cons, how does mutation testing work, unlike this guy? It mutates copies of our code, hence the name. And it does this in order to create test failures, otherwise known as faults. So mutation testing can be categorized as a fault-based testing technique. And this means it's related to something you might already be familiar with, Chaos Monkey from Netflix. Just like Chaos Monkey uses faults to help Netflix discover flaws in their error recovery process, mutation testing uses faults to help us discover certain flaws in our test suite and in our code. But the way mutation testing does this is sort of upside down from how Chaos Monkey works. Chaos Monkey is best known for injecting faults, like jitter and lag and so forth, into Netflix's production network. If Netflix's customers don't notice if all goes well in that Netflix's customers don't notice and their metrics still look okay, then Netflix knows that their error recovery is working okay. But mutation testing instead injects semantic changes, not necessarily faults. We hope that every one of these will create faults, but that's up to the test suite. It injects them into copies of our code, not our actual network, and it does this in our test environment, not production. Whew. And if all still goes well, in the sense that our tests all still pass, that does not mean all is well. That means that there is a problem. Remember, every change should make at least one test fail. Mutation testing has also been compared to fuzzing, that security penetration technique I mentioned this morning, involving throwing lots of random data at an application. But mutation testing is more like fuzzing our code rather than the data. Plus, it's not random. These tools have sets of mutations they know how to do, so the smarter ones can realize that they can use the results of a simpler one to not bother with a more complicated or expensive one. So they may sometimes look like they're doing something a little different, but they're not really random. They're just being smart about it. But enough about differences. What does mutation testing actually do and how? Let's start with a high-level view. First, our chosen tool breaks our code apart into pieces to test. Usually these are going to be our functions, or our methods if we're using object orientation, but I'm just going to say functions. Then for each function, it tries to find the tests that cover that function. If it can't find any, then fortunately most of them will warn us, so we know we need to go add or maybe annotate some tests. Some of the others, though, will use the entire test suite, which of course is horribly inefficient. And if we're not going to skip the current function for whatever reason, then next the tool will make mutants from that function. And to do that, it looks closely at the function to see how it can be changed. And for each tiny little way it sees to change that function, the tool will make one mutant with that mutation. Once our tool's done creating all the mutants it can from mutating one function, then it'll iterate over that list. And now we get to the heart of the concept. This chart represents the progress of our tool. Unfortunately, most of them don't give us anywhere near all this information, let alone so neatly formatted, but it's a useful conceptual model, I think. So for each mutant derived from a given function, the tool runs the function's tests, but it runs them against the current mutant in place of the original function. If any test fails, this is called killing the mutant, and it's a good thing. It means that our code is meaningful enough that the tiny little change the tool made to create this mutant did have a noticeable effect on its behavior, and that our test suite is strict enough that at least one test would notice that notice that difference and fail. Then the tool will mark that mutant killed, stop running any more tests against it, and move on to the next one. Once a mutant has made one test fail, we don't care how many more it might make fail. Like so much in computers, we only care about ones and zeros. On the other claw, if a mutant lets all the tests pass, then it is said to have survived. And that means that the mutant has the superpower of mimicry, skilled enough to fool our tests. This usually means that our code is meaningless, or our tests are lax, or both, and now it's up to us to figure out how. So now let's peel back one layer of the onion and look at some technical details of how this works. First, our tool parses our code, usually into an abstract syntax tree. Some of them work on bytecode or even raw source code, but the vast majority of the ones that are actually suitable for real-world use use an AST. So let's just roll with that approach. So this code, which you don't really need to understand and remember, becomes this AST, which you also don't need to understand and remember, except to note that there are some functions rooted at the def nodes, one of which I've fleshed out in full. Then it will traverse that tree looking for subtrees, or branches, if you will, that represent our functions. And after finding them, it looks for each one's tests. Well, it looks for the test for each one in turn, shall we say. This usually relies on us developers either annotating our tests, as I alluded to earlier, or following some kind of naming convention, though sometimes these manual techniques may be supplemented or even completely replaced by having the tool look at what tests call what functions out of our own code base. So assuming that it's not going to skip the current test for whatever reason, then it makes the mutants. And to do that from an AST function subtree, it traverses that, just like it did to the whole thing. But now, instead of looking for even smaller subtrees to extract, like twigs or something, now it's looking for nodes where it can change something. And for each node it finds, and each way it knows how to change that node, it will make a fresh copy of that function's AST subtree with that one node changed in that one way. In other words, one mutant with that one mutation. For instance, suppose it started traversing that AST for the function, and it's gotten down to this if statement. For each way the tool knows how to change that one node. It will make a fresh copy of this whole AST subtree with that one node changed in that one way. And after it's done making all the mutants it can by mutating that node, it'll go on to the next node and do the same thing there. And again until it's traversed the entire function subtree. Now I've been talking a lot about changing things. So what kind of changes are we talking about? There are quite a lot. It can change a mathematical, logical, or bitwise operator from one to another, even crossing the categories where the language allows. For instance, in many languages, we can treat anything as a Boolean and any kind of integer as a bit field. So x times y could become x and y, or x bitwise exclusive or y. It could swap the order of operands in the cases where that matters. It could change a comparison from one to another. It could insert or remove a mathematical, logical, or bitwise negation. It can remove an entire statement or expression. It can remove an if condition so that something that might be skipped around or done is always done. Taking that a step further, it can remove a looping condition so that something that might be skipped around, done once, or done multiple times is always done exactly once. It can replace a function's entire contents with returning some constant, or returning one of the arguments, or deliberately raising an error, or nothing at all, whether language permits. It could change a value to another value, like changing 42 to any of these, and many more, but I had to stop somewhere. It could even change it to something of an incompatible type, like changing a number to a, if I may quote Gollum, string or nothing. There are many, many more types of changes, but I trust you get the idea by now. Now, from here on, there are no more low-level details I want to add, so let's look at some examples. We'll start with an easy one. Suppose we have a function like this. Never mind why, it just makes a good simple example. Think about what a mutant made from this might return, because that's probably what our tests are looking at. It sure doesn't look like it would have any side effects. Mainly, such a mutant might return one of these constants or expressions. And again, many more, but I had to stop somewhere. Now, suppose we have only one test, like so. Now, this is a rather poor test. And yeah, I think at least one reason is immediately obvious to a lot of you, especially this guy who was laughing in the second row. But even so, most of the mutants on this slide would get killed by this test, the ones shown here in crossed out green. The ones returning constants are quite unlikely to match. There's no particular reason the tool would put a 4 there, as opposed to 1, 0, -1, plus and minus infinity, and the largest and smallest signed and unsigned integers and floats in various sizes and so forth. If it changed the exponentiation into subtraction, it would get us 0. Dividing them would get us 1. Returning either one alone would get us 2. And at least the deliberate errors and type mismatches would make the test not pass. But addition, multiplication, and exponentiation in the reverse order all get us the right answer. So mutants based on those mutations would survive our current test suite. So how do we see this happening? When we run a mutation testing tool, it gives us a report roughly like this. Now, the actual format is going to vary enormously, but semantically, the information should be roughly the same. And to unpack it, it's telling us that if we change the function called power in file demo.py, line 42, in any of 4 different ways, then all its tests would still pass. And then it goes on to tell us what those 4 ways are. First, to change the declaration to swap the parameters. Next, to change the body to change the exponentiation into addition or multiplication, or to change the body to swap the operands of the exponentiation. So what is this set of surviving mutants trying to tell us? We can tell from a glance at the code that it's probably not trying to tell us about redundant or unreachable code. It's just one line, so that kind of problem is extremely unlikely. So it's probably a test gap. The question now boils down to, how are these mutants surviving? Are they pulling heists? Are they getting free room and board at the Xavier Institute? Or what? The usual answer is that they return the same value as the original function, at least given those inputs, or they have the same side effect, whatever it is that our tests are actually looking at. And to determine how that happens, it helps to take a closer look at one mutant and at least one test it passes. So let's start with the plus mutant. Looking at this change together with the test makes it fairly clear that this one survives because 2 plus 2 equals to 2 the 2, to 2. And so does 2 times 2, but he's in the background. We can save him for later. So how can we kill this mutant? In other words, make at least one test fail when run against that would succeed when run against the original code. What we need to do is make at least one test use inputs such that x plus y is different from x to the y. And to do that, we could either add a test or change our existing test to something like asserting that 2 to the 4th power is 16. All the mutants that our original test killed, this would still kill. But 2 plus 4 is 6, not 16. So this kills the plus mutant. You see how that works? Yeah, I'm seeing some nods out there. Good, good. For the rest of you not yet nodding, there will be a couple more examples. Better yet, 2 times 4 is 8, which is also not 16. We developers should certainly know our powers of 2 at least that well. So this kills the times mutant as well. You'll find that killing one mutant often kills many other mutants of the same function. But the pair of argument swapping mutants still survive because 4 squared is the same as 2 to the 4th. They're both 16. But that's okay. We can attack them separately. No need to kill them all in one swell swoop and be some kind of superhero about it. Once again, we can either add a new test or change an existing test, maybe to something like asserting that 2 to the 3rd power is 8. 3 squared is 9, not 8. So this kills the the argument swapping mutant. Better yet, 2 plus 3 is 5, 2 times 3 is 6, and both of those are, guess what? Not 8. So the plus and times mutants stay dead, and we don't get any zombie mutants wandering around, even if this were still our one and only test. With these inputs, the correct operation is the only simple common one that gets us the right answer. This wasn't the only solution, though. Even if we stuck to single digits, there are lots of ways to skin that flirkin. This may make mutation testing sound simple, but this was a deliberately trivial example. So let's look at a more complicated one. Suppose we have a function to send a message, like so. Send message uses send bytes to send as many bytes as send bytes could send, kind of like a woodchuck, looping around to pick up where it left off last time until the message is all sent. This is a very common pattern in communication, file reading, all kinds of software. Now, a mutation testing tool could make lots and lots of mutants from this, but one of particular interest would be this, an example of removing a looping control. Now let's suppose that this mutant does indeed survive our test suite, which consists mostly of this. There's a bit more that I'm not going to show you quite yet, dealing with setting the message size and then actually creating the message. But even without seeing that, what does the survival of the non-looping mutant tell us? If a mutant that goes through the loop once acts the same as our normal code, as far as our tests can tell, then our tests are only making our normal code go through that loop once. So what does that mean? You'll find that interpreting mutants involves a lot of asking yourself, so what does that mean? Often deeply recursively. In this case, it means we're not testing sending a message larger than send bytes can handle in one chunk. There are many ways that can happen, but we're only going to look at two possible cases. The most likely is that we darn well know or should have known that we should have done so, but forgot or just didn't bother. For instance, here we have a maximum chunk size of 10,000 bytes, and yet, for whatever reason, we're only testing with an itty-bitty 3-byte message. The obvious fix in this case is to deliberately use a message larger than send bytes can handle in one chunk. And with this kind of fake messaging, it's trivial to do so. We take our maximum chunk size, add any amount, and make that big a message. But now let's look at another possible cause and solution. Suppose we did test with the largest permissible message out of a set of predefined messages, or at least message sizes. For instance, here we have small and large message sizes, and we tested with a large, and yet this mutant survives. In other words, we're still sending the message in one chunk. What could be wrong with that? It sounds like a good thing to me. What is the mutant trying to tell us in this case? In this case, it's trying to tell us that a version of send message with the looping removed will do the job just fine. If we remove the looping, we wind up with this, and now some other stuff is clearly redundant because it was only there to support the looping in the first place. And if we remove that as well, we wind up with this. And now the ultimate message is much clearer, that the entire send message function may well be redundant. We can just use send bytes directly. Now, in real-world code, as opposed to example code, maybe not, because there might be some logging and error handling and so forth that we need to put in send message and can't realistically shove down the stack into send bytes. But at the very least, the looping in send message was redundant. Fortunately, when it's this kind of problem with redundant or unreachable or otherwise ineffective code, the solution is clear and simple. Just rip out the extra junk that the mutant didn't have. This will also make our code more maintainable by getting rid of just useless cruft that's just getting in the way of understanding it. So now that we've seen some examples of finding bad tests and redundant code, I'll answer some occasionally asked questions. Mutation testing is still rare enough that I don't think there are many frequently asked questions. First off, this sounds really weird, deliberately making tests fail to prove that the code succeeds. Where did this whole bizarro idea come from in the first place? Mutation testing has a surprisingly long history, at least in the context of computers. It was first proposed in Richard Lipton's term paper titled Fault Diagnosis of Computer Programs in 1971 at Carnegie Mellon University. The first tool appeared in 1980 as part of Timothy Budd's PhD work over at Yale instead. But even then, it still wasn't practical on typical developer-grade machines of the day. That didn't happen until about the early 2000s with significant advances in CPU speed, multi-core CPU, larger and cheaper memory, and so forth. And nowadays, it's practical even on fairly low-end, but at least relatively modern, machines such as this very MacBook Air from 2020. And that leads us to the next question. Why is it so CPU and memory intensive? We need to do some math to answer that, but don't worry, it's pretty basic. Suppose our functions have, on average, about 10 lines each, and each line has about 5 places where it can be changed to any of about 20 alternatives. That works out to about 1,000 mutants per function. And for each one, we'll have to run somewhere from one of its unit tests, if we get lucky and kill the mutant on the first shot, all the way up to all of the function's unit tests if either we kill it on the last shot or it survives. Suppose we wind up running just 1/5 of the tests per function on average. Since we start with 1,000, that still winds up being 200 times as many test runs as just running the unit test suite, just running the test suite. Not necessarily unit, could be some integration tests in there and so forth. But anyway, if our tests normally take a zippy 10 seconds, that means that with these assumptions, mutation testing will take somewhere around 2,000 seconds. That may not sound like much because I'm saying seconds, but do the math and it's over half an hour. I don't want to sit and wait for that. But there is some good news. Over the past decade or so, there's been a lot of research into trimming down the number of mutants, mostly by weeding out those that are redundant with some other mutant, or perhaps with the original code, or just, what's the word I'm looking for? Trivial in some other manner, such as raising an obviously uncaught error condition. And techniques like this have trimmed down the mutant horde down to about 1/3 in some cases. But even with that rare level of success, it's still no silver bullet, because this takes a lot of CPU time itself, and there's still a lot of mutants left to deal with. The next question is, why change each mutant in only one way? And there are multiple reasons. First, the main theoretical underpinning of mutation testing is what's called the competent programmer hypothesis. So let's put that to a quick check. Raise your hand if you're competent. Okay, seeing a lot of hands out there. Those of you who didn't put up a hand, you probably actually are competent. So you might want to read up on imposter syndrome. Oh, sorry, I forgot to switch the slide. There we go. Long story short, the competent programmer hypothesis is the idea that we developers usually have a pretty good clue what we're doing most of the time, and when we mess up, it's usually one small mistake, like comparing using less than or equal to when we really should have been saying strictly less than, or maybe we got it backwards and it should have been greater than, or whatever. Does this kind of simple substitution sound familiar? Yeah, it's exactly what a mutation testing tool does. So in this sense, you could think of mutation testing as sort of a did you mean function, kind of like when Google gives you some other search if yours didn't have many hits. There are also practical considerations. For one thing, it helps us poor humans focus. It's much easier to tell what a mutant is trying to tell you if we're only talking about one thing in the first place. Another reason is that multiple mutations might balance each other out, leading to more false alarms. And lastly, allowing multiple mutations could create a combinatorial explosion of mutants, with the tool making several orders of magnitude more mutants per function, making it even more CPU and memory intensive. But we can avoid this huge workload and the lack of focus and the increased false alarms if we just limit it to one. Lastly, a more practical question: where do we fit this into our development process? Mainly, I think it belongs at least here as part of the requirements to get a pull request or merge request or whatever your process calls it or uses to be approved to merge into the main branch or however you get it published. We can set some standards for what we're willing to tolerate, such as no surviving mutants on new code and no increase of them in old code or whatever. Ideally, this would be done as part of a continuous integration pipeline that would be kicked off automatically when the PR or whatever is created and stop it if the criteria aren't met. That said, personally, I would also do it as part of the linting step, where I apply all sorts of other quality checking tools to make sure my code is as good as it can be before making anyone else bother about it. If you'd like to try mutation testing for yourself, here is a list of tools for some popular languages and platforms and some others. I doubt many of you are doing Fortran 77 these days. Don't worry too much about pictures. The last slide actually has the URL for the whole deck. The tools I know are outdated, are crossed out, but there may be many others. I don't know or follow quite all of these. To summarize at last, mutation testing is a powerful technique to help ensure that our code is meaningful and our tests are strict. It's fairly easy to get started with in terms of things like setting up the tools and annotating our tests if need be. Yes, that's probably rather tedious and time-consuming, but at least it should be conceptually easy. But it's not so easy to interpret the results, nor is it easy on the CPU. And even if these drawbacks mean it might not be a very great fit for our current projects right now, I still think it's just a really cool idea in a geeky kind of way. If you have any questions, I'll take them now. If you think of anything later, there's my contact information plus the URL for the slides, as I mentioned, complete with a full script, which I've mostly stuck to. So, any questions? I think we have a live microphone down here. There we go. Okay.
Yeah, okay. So this example with power is you showed that swapping arguments should lead to failure. But what if our argument to the function or branches in our functions are like okay with that? I mean, we merge into arrays or adding two numbers, something like this. Would we be annotating our test suite like with a huge wide list of mutants, or how it's solved?
Okay, if I understand the question rightly, it's basically sometimes swapping the arguments to whatever operation may be perfectly okay. Like if you're adding rather than doing exponents, well, in that case, you're probably not going to be bothering with a test that's the same on both sides, so that swapping them really makes, well, it would be expected to make any difference to the test results. If you did happen to have one like that, that might be one of those cases where you might get a false alarm, or the tool might be smart enough to weed that out.
But is there an annotation that would prevent certain types of... To continue the question and maybe to complement, is there a specific annotation that you could introduce around that line to hint that no mutant should be produced for that type of change?
Okay. Well, that's the kind of thing that will vary enormously depending exactly which tool you use. I don't recall seeing such a mutation, such an annotation in the particular ones I've used. I get the impression this conference is fairly Java heavy. I have not touched Java since about the late 1990s. And didn't start doing mutation testing until well after that. So I'm not familiar with the tools that exist for Java. I've heard that some of them, in particular Pit, I believe, is the main one, is very good. I would not be surprised if it had such a thing. So the short answer is I don't know. The slightly longer answer is check the docs for your tool in question. But I wouldn't be surprised if there is such a thing for at least some tools. Any more questions? We've got about 5 minutes. Okay.
Thank you. I have two questions. First one is, can we consider mutation like over-engineering? Because we will create tests in a way or where your function can evolve, but in any way your function can never evolve in this way. So you will create unit tests to protect your function that's not useless, but in a way that's never happened. That's my first question. The second one is, with LLM that generates unit tests automatically, will the perfect unit test will be generated by these LLMs with mutation and all the other things that you can improve with it?
Okay, let me try and tackle that question, the first question first. It said, can we consider mutation testing some word I didn't quite catch? Can you repeat that?
Over-engineering.
Over-engineering. Oh, yes, certainly if your program is rather trivial, then something like this may well be over-engineering. But sometimes that's what we do best, you know? And as for LLMs, yeah, that's an interesting question. I've seen some rather impressive stuff done by these LLMs. Even though they basically boil down to Markov chains on steroids and don't really understand anything, it's amazing what we've managed to encode into our use of language, whether English or Python or whatever. So, yes, I could envision some cases where an LLM might be able to look at the results of mutation testing and say, you need a unit test to tell this mutant apart from the original code and suggest such a thing. If any of you are so inclined, feel free to experiment with that and let me know how it goes. Did that answer your questions? Okay. Anybody else? Well, I'm still up here with the mic. Oh, way up there. Okay.
So my question is it possible for a mutant to modify the test, modify the code such that the test takes too long, or maybe even doesn't terminate at all? And in that case, how does the test suite proceed?
Okay, that's actually a subject I addressed in the very first version of this talk and chopped out from most of the the further ones. So it didn't seem most people were interested in that, but the short answer is yes, it is certainly possible for something such as especially the removal of conditions within a looping condition to result in an infinite loop. There are many ways you can then handle this. I think some of the tools do automatically apply a timeout, and if the one you're using does not do that for you, you can certainly add a timeout on your individual tests. At least with most languages. I've seen some testing frameworks that don't have such a feature. You could cobble that together manually, I suppose. So, long story short, yes, it is possible. How to handle it, again, as usual, depends on the tool, but can be handled in various ways. Okay. Conveniently located close question.
Have you came across the post-build, post-deployment mutation testing? When you already have the app deployed to the cloud and then end-to-end integration tests, for example, run against it?
Post-deployment whole app mutation testing seems to me like something that would certainly be possible, especially if something is taking data over an API as opposed to some human clicking and filling in fields and whatnot. I have not personally heard of that being done, but would not be surprised if somebody's tried it. Now you got me wondering how it would actually produce mutants in an efficient manner, since it would have the entire code base to deal with. I suppose for a relatively small system you could do that somewhat efficiently. For a large program, I think there are other techniques that would be better, like fuzzing and fairly standard security penetration techniques, as opposed to mutation testing, which is more aimed at the very lowest, well, not the machine code necessarily, but at least the source code that the humans have written.
I often find quite a lot of tests using a lot of mocking, and actually it doesn't actually call the real code. Do they also modify the mocks, mutation testing?
Generally speaking, no. Mutation testing tools don't modify the tests. If you have misconfigured it, it could maybe run amok and modify some of the stuff in your test directory, such as the mocks. But usually, no. How you got me wondering, would it be useful to actually make it do so? I think that would just lead to a lot of confusion. But if anybody out there can come up with a good use case that might be useful, yeah, let me know. Any more questions? We probably have a few minutes left. No, I'm being told we're out of time. Okay, thank you very much. Don't forget to vote about the talks.